So in this video, we will discuss about the try to derive the expression for partition function of a classical ideal gas in the two-dimensional case. In the one of the previous videos, we have already done it for the three-dimensional system. Here we are allowing the movement of the ideal gas particles only in two dimensions. So basically you can try to do the derivation yourself and cross-check with what I'm trying to do in this video. So my suggestion is that you try to do it yourself. So what you have to do is that you have to solve the partition function for a classical ideal gas where the particles are allowed to move only in two dimensions. So you can try to solve that yourself and cross-check with the derivation which I am trying to do in this video. Okay, so you can stop the video there and do it yourself and come back. Okay, so let me hope that you must have done your attempt to derive that partition function. So now let me try to help you to find out the solution. So what was the initial equation which we had generally for a partition function for a canonical ensemble? That expression was QNVT is equal to or even we can utilize straight away the expression which we derived for a for any kind of systems, right? Let me note down that expression for you. Yeah, so the expression was that integral 0 to infinity e raised to minus beta e GE. So that was the expression with which we started, and for a three-dimensional classical ideal gas, we have written the expression QNVT is equal to 1 by h raised to 3n n factorial integral e raised to minus beta h qp d omega. So this was for a three-dimensional case, right? And you know how did we got the d omega by h raised to 3n n factorial and all that. So based on that, here instead of the three-dimensional spherical phase space, we will consider here a two-dimensional circle in which these n particles are allowed to move through. So naturally our number of microstates, the distinct microstates, we will talk in an area element. So at that area element now we will denote it by say dA. Okay, since this is a two-dimensional situation. So here we have to, instead of d omega, we have to modify that expression by using dA. So therefore we can write down the expression as QNVT is equal to 1 by h raised to 2n n factorial integral e raised to minus beta h of qp dA. So this is the expression with which you should be starting with. And what we did that time, h of qp was substituted as p squared by 2m And then I did the integration with the product of the integration quantities. So therefore I can write Qn Vt is equal to 1 by n factorial h raised to 2n integral e raised to minus beta squared minus beta, right, minus beta by p squared by 2. So therefore I can write it as sum over pi squared product of I equal to 1 to n d squared qi d squared pi. And now I need not explain you the other things. So what do? You do the derivation of the, you do the integration of the space quantities. So in the double integral dx dy, because we are talking only about the area here, integral dx dy. So I call it as L squared. So double integral dp x dpy. So we can do it the same procedure which we did during the three-dimensional case, where you can always approximate a momentum space, and then you can call the corresponding quantities as p and p minus dp, where this area is dp. This shell, the thickness of the shell is dp. So therefore I can calculate the area and then of the shell, and then integrate it simultaneously. So what will it be? So I can write dx dpy is equal to pi p squared plus 2 pi p squared dp plus pi dp squared minus pi p squared, right? Because this is an area. And then I can write it as just 2 pi p dp right. This is 2 pi p dp, and we have neglected the quantities with dp squared. So therefore we substitute that, right? You can try it yourself. Qn Vt is equal to L squared raised to n divided by h raised to 2n n factorial integral e raised to minus beta squared by minus b the minus p squared by 2m kt, right? Minus p squared by 2m kt into 2 pi m, so 2 pi p dp raised to n. So if we assume that the p squared is equal to x, then 2p dp is equal to dx, right? So therefore I can substitute that over here and write it as equal to pi L squared raised to n divided by h raised to 2n n factorial, right? Integral 0 to infinity e raised to minus beta x divided by 2m dx raised to n, right? And this is what I get. Now I can try to simplify it further. Further, using basic identities, integral 0 to infinity x raised to n e raised to minus alpha x dx is equal to n factorial alpha raised to minus n minus 1. So this is a general expression, and if in case you don't have the alpha e raised to minus alpha x, right? So I can then write the expression as integral 0 to infinity x raised to n e raised to minus x dx is equal to n factorial, right? So I take the alpha as 1. So I can now use this expression over here. For this equation, I can use this identity. So I substitute this over there, then there x raised to 0 is equal to 1, and that means n is equal to 1 if I need to substitute this over there, right? Because I don't see a x raised to n quantity there, so I just take it as 1, then my n should be equal to 1. So therefore I can ultimately write QNVT is equal to pi L squared raised to n divided by h raised to 2n n factorial 0 factorial, right? And beta by 2m raised to minus 1 raised to n. Right. So therefore I can so what is 0 factorial? It is 1, right? So therefore I can write down that expression as pi L squared raised to n divided by h raised to 2n n factorial 1 by 2 pi m, not 2 pi, it is 2m, 2m kt raised to minus 1 raised to n, because 0 factorial is equal to 1. So therefore I can write pi L squared raised to n divided by x raised to 2n n factorial 1 by 2m kt raised to minus n. I can take it to the numerator. So therefore L raised to 2n 2 pi m kt raised to n divided by h raised to 2n n factorial, right, is equal to 1 by n factorial b raised to 2 by 3 divided by h square 2 pi mkt raised to n. So express it in terms of the lambda. So this is one of the final expressions. If I need to express in terms of lambda, I can approximate this as 1 by n factorial v raised to 2 by 3 divided by lambda square raised to n. So that's it. So this is the partition function for a classical ideal gas in the two-dimensional situation. So this expression you must have found out by yourself when you try to do it yourself. So that's it. So we will try to I will try to give a flavor of the other thermodynamic parameters which we can evaluate using QN in the next video, such as AS, the Helmholtz free energy, entropy and all that. We will try to do a short video after this. Okay.